Hello, my name is Cutrona, and I am a museum educator at the National Museum of the United States Army. Today, we are going to be talking about the accomplishments of the Eniac and the women computing pioneers who played an instrumental role in programming the Eniac during World War II. Winning World War II required an all-out effort. Thousands of women on the home front answered their country's call to join the military, industry, and the civil service. In 1943, the U.S. Army recruited female mathematicians to set up and operate the Army's newest top-secret weapon, the electronic numerical integrator and computer, also known as the Eniac. These unsung heroes wired the electrical connections that enabled the world's first electronic digital computer to complete 300 calculations per second. In doing so, they built a framework for the field of computer programming. We are going to discover how the female computers, as they were known, solved complex problems, contributing to Army innovation during World War II, and how, in recruiting these women, the Army created new professional opportunities for women in the field of computer programming. We're going to begin today's program by briefly looking at the United States' entry into World War II. War broke out in Europe in 1939. Many in the U.S. were worried about the impact that the war would have at home. Then, in December of 1941, the Japanese Air Force bombed Pearl Harbor, Hawaii, and war was declared. The U.S. military, however, was not ready. It didn't have enough people or the up-to-date equipment to fight an all-out war. Leadership knew that they had a big job ahead to get up to fighting strength. The Ordnance Department of the Army had a special challenge. It was responsible for the design, development, procurement, storage, and issue of all the Army's combat material and munitions. As the country mobilized, so did the Ordnance Department. Ordnance needed to secure large amounts of war material, and it needed people to be able to do this. The Department of Defense would have to find many workers very fast and compete with other government agencies and private manufacturers to do so. As a part of the nation's general wartime mobilization, President Roosevelt signed Executive Order 9139 on April 18, 1942, which established the War Manpower Commission. The Commission's directive was to formulate plans and programs and establish basic national policies to assure the most effective mobilization and maximum utilization of the nation's manpower in the prosecution of the war. They also had to estimate the requirements of manpower for industry and review all other estimates of needs for military, agricultural, and civilian manpower. In order to assure the most effective mobilization and maximum utilization of the nation's manpower in the prosecution of the war, the War Manpower Commission estimated that nearly 7 million new workers would be needed in 1942. Now, as you take that number in, 7 million new workers, the question becomes, why were there suddenly so many new jobs? The factors are twofold. The war created a huge demand for new workers. Thousands of men and women joined the military, leaving behind their farm, factory, mill, and office jobs. At the same time, factories switched from making things for people to producing things to fight the war. And government agencies suddenly had a host of new war-related assignments. The military, factories, and the civil service all needed people right away. This led to the war manpower shortage. The War Manpower Commission looked for new sources of labor for these war jobs, and women were one of those new sources of labor. Now, I will say that women were not necessarily the first choice of workers for these jobs. But the War Manpower Commission's Women's Advisory Board suggested that they recruit women. And with a huge need for workers, government agencies and private businesses are going to become much more welcoming to women workers than in the past. To provide some background context for the rest of the program, we are going to talk about women's participation in the labor force before and during World War II. We're going to start by looking at a chart that examines women as a permanent part of the labor force from the late 19th century through World War II. On the chart, we can see that in 1940, just before Pearl Harbor, women made up about 24% of the labor force. Looking at the chart again, we can see that in 1890, only around 17% of women participated in the workforce. So there was a steady rise in women's labor force participation from the end of the 19th century to the 1940s, with women making up around 32% of the labor force by 1944. Let's go ahead and take a look at another chart. This chart breaks women's participation in the labor force down into two categories: single women and married women. In 1940, about 38% of single women were employed. Only 13% of married women worked for wages. However, married women made up more than half of the female workforce because there were more married women than single women. By the end of the war, 53% of single women were employed versus 22% of married women who worked for wages. As we can see from these charts, the war increased women's overall employment for both single and married women, and women's employment continued to rise through the end of the 20th century. However, there was still a disparity in the percentage of single women versus married women who worked for wages. So why did married women come and go from the workforce? Through the 1930s, social pressure forced women to leave. There was a general disapproval of married women working. Many companies and governments would not hire married women. For example, the vast majority of school districts wouldn't hire married teachers. Federal civil service policies in the 1930s discouraged employing both husbands and wives in federal positions and encouraged the firing of one or the other. It was generally the wife that was let go. But during World War II, the war is going to bring a temporary pressure for married women to come back into the workforce. Here are two government propaganda posters. What message are they sending? One thing that might stand out to you is the idea of equating women's work in the labor force with patriotism or their patriotic duty. We still haven't answered the question yet, what job did these women hold? Now, women were found in many different occupations, but half of all women workers are concentrated in relatively few types of occupations. Here is a chart that lists the 10 largest occupations of women from 1900 to 1950. In 1940, we can see that stenographers and typists, private household workers, saleswomen, teachers, bookkeepers, and waitresses are some of those occupations that women were concentrated in at the time. Now, one of the reasons that women were clustered in a small number of fields was due to their educational opportunities. While women received a majority of high school diplomas in 1900, post-secondary education was still reserved primarily for men. Women earned only 19% of bachelor's degrees in 1900, but their share doubled to 40% by 1930 and remained at about that level in 1940. If you add in 2-year degrees, which is what you needed to be a school teacher, then women made up a bit less than 50% of college students. So there are a lot of educated, talented women available for the workforce as the U.S. is entering World War II. As I mentioned earlier, the government campaign is going to ask people to consider women's work as a temporary patriotic measure. The idea is that women would step out of their usual domestic roles to help win the war. Then they would go right back. And millions of women responded. After the war, while many women did leave the workforce, either voluntarily or they were let go from it, overall women's employment continued to grow. Now that we've had a chance to examine women's participation in the labor force before and during World War II, let's turn our attention back to the Ordnance Department. The number of civilians in the Ordnance Department grew during World War II from 27,088 to 262,000. Women workers accounted for approximately 85,000 of the civilian workforce. The Ordnance Department needed a lot of workers because they had big responsibilities. The Ordnance Department's first challenge was to buy a large amount of equipment to fight a war. This is a picture of the Aberdeen Proving Grounds in Maryland. It's here that the department tested all of the material that would be used by soldiers. It had to work and work well. Their job was to make sure that soldiers had what they needed to execute their mission and to win the war. Ordnance bought weapons. They had to test the weapons and make sure that soldiers would know how to use them. One of the challenges was to accurately aim and fire guns. These are large guns that fire shells over very long distances, like this howitzer pictured here. The problem isn't where the shell goes up, it's determining where it's going to land. In order to figure out where it will land, or essentially where you want it to land, mathematicians use numerical integration to calculate the path of the projectile from the time it leaves the muzzle of the gun until it reaches the ground. One way for us to visualize the pathway or trajectory of a projectile and the importance of hitting the right target is to think about the game Angry Birds, which follows a similar principle. In this case, the projectile is an angry bird and the target is a pig, or the structure surrounding a pig. Now, before you launch your Angry Bird, you have to think about the velocity and the angle of the slingshot in order to make sure that your projectile or bird is going to follow the correct trajectory to hit the right target, as we can see with our Angry Bird image on the screen. Now, in calculating the pathway of a projectile, you also have to account for other factors, such as wind, weather, elevation, and air resistance. Now, aiming to hit the right target is important, but as we can see with the factors mentioned above, finding the right angle to fire a weapon to hit the right target was a complicated process. Today, weapon systems have computers that calculate how to aim. During World War II, the Army produced books of charts called firing tables that would tell a soldier how to aim based on where he was in relation to the target. Now, somebody had to calculate the tables. The Army hired hundreds of women, many of who were former school teachers, to work as computers to figure out the calculations for ballistic trajectories. At the time, computer was a term used to describe people who did mathematical calculations. Now, this was considered a woman's job, kind of like being a clerk, even though they needed a strong background in advanced mathematics. It was so hard to find enough people that the Army trained women, like these pictured here, in the skills that they needed to be able to calculate the firing tables. It was very slow work done on mechanical calculators. In fact, it could take a skilled person at least 20 hours to calculate a 60-second trajectory. This machine pictured here is a differential analyzer. It's essentially a giant mechanical calculating machine. It could produce a trajectory in around 15 minutes. But the Ordnance Department only had 2 of these. So the Ballistics Research Lab and its human computers couldn't keep up with the increasing demand for tables. The requests were coming in at a rate of 6 new tables a day. The Army needed to speed up the calculations. Problems need solutions. Army Captain Paul N. Gillen, then in charge of ballistic computations at the Ballistics Research Lab, asked for Lieutenant Herman H. Goldstein to be assigned as supervisor of the computational and training activities in Philadelphia at the Moore School at the University of Pennsylvania. Goldstein, who had a PhD in mathematics, along with the firing table personnel, are suddenly rubbing elbows with a talented group of scientists and engineers in Philadelphia. Among them are physicist Dr. John W. Mauchly and an engineer named J. Presper Eckert Jr. Mauchly proposes to the group that they invent an all-electronic calculating machine. So a seed of innovation is being planted as the Army is looking for a solution to its firing table problem. The Ballistics Research Lab and the Moore School would go on to develop what would become the first electronic, digital general-purpose computer. It was called Eniac, which stood for the Electronic Numerical Integrator and Computer. The Eniac was once described as a collection of electronic adding machines and other arithmetic units which were originally controlled by a web of large electrical cables. Now you can see in the diagram how the Eniac was laid out, and hopefully it gives you a sense of how large this machine was, taking up the majority of a large room. While the Eniac's hardware was designed by male scientists and engineers, women drafted the construction plans, assembled and wired the components. Unfortunately, most of them have since been forgotten. So we're going to talk about some of them today. There is Adele Goldstein, Herman Goldstein's wife. She was an accomplished mathematician in her own right. She was brought onto the project and eventually wrote part of the Eniac's technical manual. 6 women were also hired from the computer pool to set up and operate Eniac. They were Kathleen K. Bignulty Mauchly Antonelli, Betty Jean Jennings Bartik, Frances Fran Bilas Spence, Frances Betty Snyder Holberton, Ruth Lichterman Teitelbaum, and Marlon Westkoff Meltzer. These are Betty Jean Jennings on the left and Fran Bilas on the right, operating Eniac's main control panel at the Moore School at the University of Pennsylvania. These women played a key role in the invention of computer programming. We are going to talk about this role as we look more closely into some of the basic building blocks of how the Eniac operated. And we're going to start with wiring, because wiring is key to electronics. Eniac and all computers work by transmitting electrical pulses around a circuit. So here we have a diagram of a circuit. With circuits, power moves from a power source. In the case of our diagram, that power source is a battery. So the power is moving from the battery across the wires and then back to the power source or back to the battery. Now, along the way, as the electricity is flowing, it may create an event. In the case of our circuit, because there's a light bulb that is a part of the circuit, as that electricity is flowing, the light bulb would actually be illuminated. Now, another important part of a circuit is the switch, and you can identify the switch on the upper middle portion of the diagram. Now, a switch can be in one of two positions. It can be open or closed. When a switch is open, the power is interrupted, so the electricity is not flowing from the power source back to the power source, and in this case, our light bulb would not be illuminated. Let's go ahead and take a look at this circuit. It's very similar to the diagram that we just looked at. Here we have our power source as our battery. We have the snap circuits allowing the electricity to flow. We also have our light bulb and our switch. Now notice that our switch is currently in the off or open position, so our light bulb is not illuminated. But if I go ahead and turn the switch to the on or closed position, you can now see that our light bulb is lit. So one important thing to keep in mind when we're talking about circuits in the Eniac is that the Eniac would not have been able to operate the way that it did without its electronic circuits. Now that we've had a chance to talk about circuits, the next question becomes, how was the Eniac programmed? Unlike computers today, the Eniac had to be directly programmed, which was a complicated process. The problems that the programmers ran on the Eniac were complex, so before even setting up the problem itself had to be broken down into individual steps that the Eniac could process. Then the programmers directly programmed the Eniac by wiring circuits and setting switches to direct power through the hardware. And you can see the wires in the image here. Now, a number of wires had to be plugged in for each single instruction of a problem. Thousands of them each time a problem was to begin a run. So this would take several days to set up and then many more days to check to make sure that the problem was running as it was supposed to. Now, you may be wondering, how did the women learn how to program the Eniac? Well, we have a short clip of an interview with Kay McNulty, one of the original programmers, so I'm going to let her explain in her own words what this process looked like.
We were told that we had to learn what we could so that we would be able to program the Eniac. What for? To do trajectories. Well, why do they want trajectories? Well, that was what it was built for, so that's what we were going to do. So no manuals had been written, none whatsoever. So some of the engineers who worked on the project gave us their great big blueprints, their wiring diagrams and their block diagrams and things, and we worked our way through these things to find out what every tube would do.
As we heard from the interview, before the female programmers learned how to program the Eniac, they first had to figure out how the Eniac worked without having access to the computer itself or even to a manual for the machine. Instead, the women had to teach themselves about the Eniac through diagrams like circuit diagrams and block diagrams, and when available, information from the engineers involved in designing and building the machine. During her work programming the Eniac, Kay McNulty was credited with the invention of the subroutine. Subroutines cut down on setup time when two problems have similar pathways. So this is one example of innovation that came about through developing the Eniac. We're also going to briefly talk about the Eniac's data input and output. Now, data was not typed in on a keyboard, rather it was fed in on punch cards. the card stores data through a code or punches entered on the cards. We have an example of a punch card here. Now with this punch card, each alphanumeric symbol is designated by binary code punched onto the card. Binary code has two values, on or off, 0 or 1. This is an example of a binary code alphanumeric system. The numeral 1 in this 8-bit binary code is 00110001, and it's outlined in red. So if you had a stack of cards, you could write a message to your friends, and at the bottom of the screen, we've actually written a message in binary code. If you take the time to decode it, you'll see it says, "Go Army." Next, we're going to turn our attention to the Eniac's main unit, the accumulator. Now, the Eniac had 20 accumulators. Each accumulator was capable of storing and adding a 10-digit number because each accumulator had 10 decade counters. The woman with the largest computer board on the far left-hand side of the image is holding the originally sized array of tubes for 1 decade counter, which represents 1 digit. The Eniac's decade counter used 10-position ring counters to store the digits 0 to 9. Arithmetic was performed by counting pulses with the ring counters. So when a decade counter received an electronic pulse, it would advance the ring counter by a stage. Now, you may have noticed with the image of the decade counter, the vacuum tubes. The Eniac actually had around 18,000 vacuum tubes, like the one pictured here. Now, as you may have been able to guess with that large number, the vacuum tubes played an important role in how the Eniac operated because the vacuum tube worked as the Eniac's electronic switch. Now, if you remember from earlier when we talked about switches, switches play an important role in the circuit helping to control the flow of electricity. And so that's what the vacuum tube did for the Eniac. And the vacuum tube was one of the reasons, as an electronic switch, that the Eniac was able to operate as quickly as it did. When it was up and running, the Eniac could do 300 multiplications a second. It took 30 seconds to calculate a firing trajectory of a 60-second shell launch. Remember, it took at least 20 hours to perform the same calculation manually. Now, work on the Eniac goes from 1943 to debugging in 1945, and it had an experimental period in 1946. It was then moved from the University of Pennsylvania to the Aberdeen Proving Grounds in 1947. So it missed the war. But during the period 1948 to 1955, when it was retired, the Eniac was operated successfully for a total of 80,223 hours of operation. In addition to ballistics, fields of application included weather prediction, atomic energy calculations, cosmic ray studies, thermal ignition, random number studies, wind tunnel design, and many other scientific uses. And the development of the Eniac led to further innovation to shrink the computer and make it faster by using better parts. First the transistor, and then the integrated circuit chip. That's why today your cell phone has more computing power than the Eniac. The work of women computers became the basis for computer programming. That work allows you to do all kinds of things with your cell phone or laptop today, including broadcasting this program. And that's why it's important to continue to remember these women's story as they truly were pioneers in the field of computer programming. Thank you for watching today's program, and feel free to visit our website for more information.